Hey guys, Professor Doney back. We're in the middle of talking about electric potential and charged particles and Coulomb's law and electric fields, and this is just the next video. Our last video was on electric field strength due to point charges. We had two of them, and we're going to use that similar configuration here. We're going to have the +1 Coulomb up here, the -2 Coulombs down here on a 3, 4, 5 triangle, and we're going to want to know what's happening, what the voltage is at point A. Now again, I'm using a full Coulomb for the charges, which is kind of unrealistic. Typically it's microcoulombs times 10 to the -6, but just trying to keep the math easy as we go through these calculations. So make sure you're up on your scientific notation and dealing with those. So want to find the voltage. The nice thing about voltage versus Coulomb's law of force and electric field strength is voltage is a scalar. That means we don't worry about the sine, cosine, angle business. We just need to put them together. So if we want to find the total voltage at A, we're going to have to add up, or summation, all the KQ over R's due to each one. So we're going to need to find the voltage at A due to 1 and the voltage at A due to 2. Now, how do we deal with the plus minus? Well, we're going to add that one at that point, and we'll end up minusing this one because it's the minus charge there. So we might have a something minus a something to give us the total charge at A. Now, what else to keep in mind just as we look at what our answer would be? We are closer here, so we'd expect more of an influence from this charge down here, this lower charge, than the upper charge. Also, it is twice as big, so we're expecting more of an influence twice, 2 times, not so much multiplying 2 times, but that this would have quite an influence on the answer here, so possibly looking at a negative voltage there. Okay. Now again, these voltages are scalars, so they'd be along the equal potential line, but we can go ahead and calculate them. What's the voltage due to 1? Well, it's KQ over R. That's 9 times 10 to the 9th. Has a voltage of 1, or sorry, a charge of 1 Coulomb, a distance of 4 meters. Alright, if I go through that, it's basically 9/4 times 10 to the 9th, and that has units of volts. Alright, the second one here, let's just make it a different color so it stands out a little bit. There's a pretty silly color. We're going to have 9 times 10 to the 9th. This is the -2 charge down here. Times 2 coulombs, because that's the charge strength, over a distance of 3. So that comes out to be 3 times 10 to the 9th, or to that, 18 over that, actually becomes out to be 6 times 10 to the 9th volts. Alright, since that is a negative charge, this will be minus here. We take 9/4 minus that 6, which 6 is basically 24/4, so we have a common denominator, if you remember doing that. 9 minus 24 gives us what? Minus 15/4 times 10 to the 9th volts at that point. Again, we're using a huge charge size of full coulombs, so we're having quite a sizable voltage going on due to those. Now, 15/4 is really 3.75, so we could write that as 3.75 times 10 to the 9th volts, and that would be our answer. Again, we don't have to worry about the sine cosine, so this is actually pretty nice for this problem. It's well, basically as straight as that. So hope that one worked out for you. I agree that these are a lot easier to deal with than the electric fields, and we'll see you in the next video.